What if Earth once had two moons, and the missing one still influences us from the shadows? Picture this. You're standing in your backyard on a crisp autumn night, looking up at that familiar silver orb we call the moon. It's been humanity's constant companion for as long as we've existed, our nightlight, our calendar, our inspiration for countless songs and stories. But what if I told you that what you're seeing is only half the story? What if, billions of years ago, Earth didn't have just one moon but two? Welcome to another episode of Javis Heist, where we dive deep into the mysteries that keep scientists awake at night and make the rest of us question everything we thought we knew about our world. I'm your host, and today we're exploring one of the most mind-bending theories in astronomy, the idea that Earth once had a second moon, and that this lost celestial body might still be influencing our planet from the shadows of space. Now, before you dismiss this as science fiction, let me tell you something that might surprise you. This isn't just some wild conspiracy theory cooked up by internet forums. This is a legitimate scientific hypothesis that's been seriously discussed by some of the world's leading astronomers and planetary scientists. And the evidence? Well, it's literally written in the rocks beneath our feet and scattered across the surface of the moon we can still see. So grab your coffee, settle in, and prepare to have your mind blown. Because by the end of this episode, you'll never look at the moon quite the same way again. Let's start with what we know for certain about our moon, because understanding the familiar will help us appreciate just how extraordinary the unfamiliar, really island, our moon, is weird. I mean, really weird. In fact, it's so unusual that for decades, scientists struggled to explain how it even came to exist. Most planets in our solar system have moons that are clearly captured asteroids. Small, irregularly shaped rocks that got caught in their gravitational pull. But Earth's moon? It's massive. It's about 1/4 the size of Earth itself, making it proportionally the largest moon relative to its planet in our entire solar system. Think about that for a moment. Jupiter has 95 known moons, but even its largest, Ganymede, is only about 2% of Jupiter's mass. Saturn's got 146 moons, but they're all tiny compared to Saturn itself. Yet here's Earth, this relatively small rocky planet, with a moon so large that some scientists argue we should really be called a double planet system rather than a planet with a moon. But the moon's size is just the beginning of the mystery. There's also its composition. When the Apollo missions brought back lunar rock samples in the 1,960 seconds and 70 seconds, scientists made a startling discovery. The moon's rocks were remarkably similar to Earth's rocks, so similar in fact that it became clear the moon must have formed from the same material as Earth. But how? This led to the development of what's called the giant impact hypothesis. Picture this. About 4.5 billion years ago, when Earth was still a young, molten world, a Mars-sized object, scientists call it Theia, slammed into our planet at an incredible speed. The impact was so massive, so violent, that it literally blew chunks of both Earth and Theia into space. These chunks then gradually came together under their own gravity to form our moon. It's a dramatic story, and for decades, it was the best explanation we had. The giant impact hypothesis explained the moon's size, its composition, and even why the Earth-Moon system has such unusual angular momentum. Most scientists were satisfied. Case closed. But then, in 2011, something happened that changed everything. A team of researchers led by Eric Asfaug at the University of California, Santa Cruz, published a paper that would shake the astronomical community to its core. They had been running computer simulations of the giant impact event, trying to understand exactly how it played out. And what they discovered was this: the impact that created our moon might not have created just one moon. It might have created two. Now, I want you to imagine witnessing the most spectacular cosmic event in Earth's history. You're somehow floating in space, watching our young planet as it spins in the darkness. Suddenly, from the depths of space, comes Theia, a world nearly as large as Mars, hurtling toward Earth at 25,000 miles per hour. The collision is beyond anything your mind can comprehend. It's not like two cars crashing, it's like two drops of molten metal colliding in slow motion. Except each drop is an entire world. The impact vaporizes rock, creates temperatures hotter than the surface of the sun, and sends billions of tons of debris spiraling out into space. For hours, maybe days, Earth is surrounded by a ring of glowing molten rock like Saturn's rings, but made of liquid stone and metal. Gradually, most of this material begins to clump together under its own gravity. The largest clump becomes what we now call the Moon. But here's where Asfaug and his colleagues made their breakthrough discovery. The computer simulations showed that sometimes, not always, but sometimes a second, smaller clump would form as well. This second moon would be much smaller than the first, maybe about 1/30th the mass of our current moon, or roughly the size of the asteroid Ceres. It would orbit Earth at a different distance, following its own path around our planet. For millions of years, Earth would have had two moons dancing in its sky. Can you imagine what that would have looked like? Two crescents hanging in the night sky, sometimes appearing close together, sometimes on opposite sides of Earth. The tides would have been more complex, creating intricate patterns that would have influenced the development of early life. The night would have been brighter, with two sources of reflected sunlight. Ancient humans, if they had existed back then, would have had an entirely different relationship with the night sky. But here's the thing about having two moons. It's not a stable situation. The gravitational interactions between Earth and two moons create what scientists call a three-body problem. And three-body problems in space tend to be chaotic. Something has to give. According to the theory, what happened next was both inevitable and catastrophic. The two moons, following their separate orbits, gradually moved closer and closer to each other. For perhaps 10 to 100 million years, they shared the sky, slowly spiraling inward due to tidal forces, and then, one day, they collided. But this wasn't the violent, explosive collision you might expect. Because both moons were made of similar material, and because the smaller moon was moving relatively slowly when it caught up to the larger one, what happened was more like a cosmic slow-motion crash. The smaller moon didn't shatter the larger one. Instead, it splattered across the larger moon's surface like mud hitting a wall. This is where the theory gets really interesting, because if this splat collision really happened, it would have left evidence. Evidence that we should be able to see today, just by looking up at the moon with a good telescope. Here's something that's going to make you want to go outside and stare at the moon tonight. If you've ever really looked at the moon, I mean really looked at it, maybe through binoculars or a small telescope, you've probably noticed that it doesn't look the same on all sides. One side is covered with dark patches that ancient people called seas. though we now know they're actually vast plains of hardened lava, while other areas are bright and heavily cratered. For centuries, astronomers just accepted this as normal. Moons have different terrain, right? But when we started studying the moon more carefully, especially after the Apollo missions, a puzzling pattern emerged. The differences between the light and dark areas weren't random. They were systematic. And they told a very specific story. The dark areas, what scientists call the lunar Maria, are primarily on the side of the moon that faces Earth. The far side of the moon, which we didn't even see until the Soviet Luna 3 probe photographed it in 1959, tells a completely different story. It's almost entirely bright, heavily cratered highland terrain. There are hardly any of those dark seas at all. Now, this asymmetry has puzzled scientists for decades. Why should one side of the moon be so different from the other? Various theories have been proposed. Maybe Earth's gravity somehow influenced how impacts affected the moon, or maybe there were differences in the moon's internal structure. But none of these explanations fully satisfied everyone. Enter the splat collision theory. If a smaller moon had indeed crashed into the larger one, and if that collision happened at a relatively low speed, it would have added a thick layer of material to one side of the moon, specifically the side that faces away from Earth. This added material would have changed the moon's internal structure, making it asymmetrical in exactly the way we observe today. Think about it like this. Imagine you have a baseball, and someone throws a handful of clay at it. The clay doesn't bounce off. Instead, it sticks to the surface, creating a thick coating on one side of the ball. That's essentially what the splat collision theory suggests happened to our moon. The smaller moon became that coating of clay, fundamentally altering the larger moon's structure and appearance. But the evidence doesn't stop there. In 2019, researchers analyzing data from NASA's Grail mission, which mapped the moon's gravitational field in incredible detail, made a startling discovery. The moon's crust is significantly thicker on the far side than on the near side. Not just a little thicker, we're talking about a difference of up to 60 kilometers in some areas. This thickness difference creates what's called a mass anomaly. The far side of the moon is literally heavier than the near side, which is exactly what you'd expect if a second moon had splattered across that surface billions of years ago. It's as if the moon is carrying the fossilized remains of its lost twin, right there on its back, for anyone who knows how to look for it. But wait, there's more. And this is where things get really intriguing. In 2011, the same year that Asfaug's team published their double moon theory, another group of researchers made a different but potentially related discovery. They found evidence that Earth might currently have what they call quasi-satellites, small objects that follow Earth-like orbits around the Sun, staying relatively close to our planet without actually orbiting Earth directly. The most famous of these is an object called 3753 Cruithne, which follows a horseshoe-shaped orbit that keeps it in Earth's vicinity. But there are others, and some of them are unusual. Now, I want to talk about something that's going to sound like science fiction, but I assure you, it's very real science fact. There are objects in space near Earth that we can barely see, that follow strange orbits, and that some scientists believe might be remnants of ancient cosmic events. Objects that could, and I stress, could be pieces of that lost second moon, still orbiting in the darkness, still influencing our planet in ways we're only beginning to understand. Let's start with asteroid 2016 HO3. Discovered just a few years ago, this object has been dubbed Earth's second moon by some media outlets, though that's not technically accurate. What 2016 HO3 actually is a quasi-satellite, an object that orbits the Sun in a pattern that keeps it relatively close to Earth. It's been following this orbit for at least a century, and it will continue to do so for several more centuries. But here's what's strange about 2016 HO3. Its composition and behavior don't match what we'd expect from a typical asteroid. Most asteroids are either rocky or metallic, with compositions that are clearly different from Earth and Moon rocks. But the spectral analysis of 2016 HO3 suggests it might have a composition similar to lunar material. Some researchers have speculated that it could actually be a chunk of the Moon that was blasted into space by a relatively recent impact. But what if it's not recent at all? What if 2016 HO3 and other similar objects are actually ancient remnants of that second moon that have been quietly orbiting in Earth's vicinity for billions of years? Then there's the mystery of the Kordylewski clouds. These are collections of dust particles that exist at two of Earth's Lagrange points, stable areas in space where the gravitational forces of Earth and the Moon balance out. The Hungarian astronomer Kazimierz Kordylewski first observed these dust clouds in 1961, but they're so faint and diffuse that their existence has been debated for decades. In 2018, however, Hungarian researchers finally confirmed that these clouds are real. Using sophisticated optical equipment, they managed to photograph the dust concentrations and prove that they exist. But here's the mystery. What are these clouds made of, and where did they come from? Some of the dust could be from comets or asteroids, sure. But some researchers have suggested that at least part of these clouds might consist of material from ancient lunar impacts, or even from the theoretical collision between Earth's two primordial moons. If that's true, then these clouds would be like cosmic graveyards, holding the scattered remains of Earth's lost twin. And then there are the truly mysterious objects, the ones that make astronomers scratch their heads and wonder if our understanding of the early solar system is as complete as we thought. Take 2020 CD3, for example. This object was discovered in February 2020, and for months, it actually did orbit Earth as a temporary mini-moon. But when researchers analyzed its composition, they found something puzzling. Its spectrum didn't match typical asteroids, and its orbit suggested it had been captured from a very specific region of space, a region that's associated with debris from the early Earth-Moon system. 2020 CD3 has since escaped Earth's gravity and returned to orbit the Sun, but while it was here, it raised some fascinating questions. Was this just a random space rock that happened to get caught by Earth's gravity? Or was it something more, perhaps a piece of primordial debris that had been quietly orbiting in the inner solar system for billions of years before finally coming home? Now, here's where our story takes a turn that might make you reconsider everything you thought you knew about the forces that shape our daily lives. Because if Earth really did once have a second moon, and if remnants of that moon are still out there in space, then those remnants might still be influencing our planet in subtle but measurable ways. Let me explain what I mean. Gravity isn't just about big, obvious effects like keeping us on the ground or making the tides rise and fall. Gravity is a fundamental force that operates at all scales, and even tiny objects can have measurable gravitational effects if you know how to look for them. Scientists have been studying Earth's gravitational field with incredible precision for decades, using satellites and ground-based instruments to map every tiny variation in our planet's gravitational pull. What they've found is that Earth's gravity isn't uniform. It varies slightly from place to place due to differences in the density of rock beneath the surface, the presence of underground water, and even the gravitational influence of the moon and Sunday. But there are anomalies. Small, persistent variations in Earth's gravitational field that don't quite match up with what we'd expect based on our current models of the Earth-Moon system. Some of these anomalies have been explained by discovering underground geological structures or variations in ocean currents, but others remain mysterious. Could some of these gravitational anomalies be caused by the influence of objects in space that we haven't fully cataloged yet? Objects like quasi-satellites, dust clouds, or even larger chunks of debris from that hypothetical second moon? Think about it this way. If you had a second moon that was roughly the size of Ceres, about 940 kilometers in diameter, and that moon was suddenly destroyed, where would all that material go? Some of it would rain down on Earth as meteors. Some would be absorbed by the surviving moon, but a significant amount would be scattered throughout the inner solar system, creating a diffuse cloud of debris that would continue to orbit the Sunday. Over billions of years, most of this debris would either be swept up by planets or ejected from the solar system entirely. But some of it, the pieces in just the right orbits, might persist, creating a kind of gravitational ghost of the lost moon. These remnants would be too small and too spread out to see easily, but their collective gravitational influence might still be detectable. There's another possibility that's even more intriguing. What if the second moon wasn't completely destroyed? What if, instead of being shattered into countless tiny pieces, it was broken up into a few large chunks? Chunks that are still out there, following dark, distant orbits that keep them just beyond the range of our current detection capabilities? This isn't as far-fetched as it might sound. Our solar system is full of objects that we haven't discovered yet. Every year, astronomers find new asteroids, comets, and other small bodies. In fact, it's estimated that there are probably millions of objects larger than 1 kilometer in diameter in the inner solar system that we haven't cataloged yet. Most of these are in the asteroid belt between Mars and Jupiter, but some follow more unusual orbits that bring them closer to Earth. A few might even be pieces of that lost second moon, following long elliptical paths that take them far from the Sun before bringing them back to the inner solar system. This brings us to perhaps the most fascinating aspect of the lost moon theory: the possibility that this ancient cosmic event is still influencing our lives today in ways we don't fully understand. Let's start with something concrete: the Earth's rotation. Our planet spins on its axis once every 24 hours. But that rotation isn't perfectly stable. Earth wobbles slightly as it spins, like a top that's starting to slow down. This wobble, called precession, occurs on multiple timescales. Some variations happen over months or years, while others take thousands of years to complete a full cycle. Scientists have identified most of the causes of these variations. The gravitational influence of the moon and sun, changes in atmospheric pressure, the movement of molten rock in Earth's core, all of these factors contribute to our planet's wobble. But there are still small variations that can't be fully explained by our current models. Could some of these unexplained variations be caused by the gravitational influence of remnant objects from the lost moon? It's possible. Even a small gravitational influence, if it persists over long periods of time, can have measurable effects on a planet's rotation, but the influence might go deeper than that. Consider the role that the moon plays in Earth's climate and weather systems. The moon's gravity doesn't just create ocean tides, it also creates atmospheric tides, subtle variations in air pressure that influence wind patterns and weather systems around the globe. If Earth once had two moons, the atmospheric tides would have been more complex, creating weather patterns that might have influenced the evolution of early life on Earth. And if remnants of that second moon are still out there, still exerting their tiny gravitational influences, then they might still be affecting our weather in ways that are too subtle to easily detect. There's also the question of Earth's magnetic field. Our planet's magnetosphere, the invisible shield that protects us from harmful solar radiation, is generated by the movement of molten iron in Earth's core. This movement is influenced by Earth's rotation, which is influenced by gravitational forces, which brings us back to the moon and its lost twin. Recent studies have suggested that the moon's gravitational influence might play a more important role in maintaining Earth's magnetic field than previously thought. If that's true, then the loss of a second moon billions of years ago might have had long-term consequences for Earth's magnetic environment, consequences that could still be affecting our planet's ability to shield itself from cosmic radiation. And then there are the more speculative possibilities. Some researchers have wondered whether the gravitational influence of a lost moon might have affected the development of life itself. The complex tides created by two moons would have created unique environments in Earth's ancient oceans, tidal pools with different rhythms, coastal areas with unusual water flow patterns, deep ocean currents that followed paths we can't imagine today. These environments might have provided the specific conditions needed for certain crucial steps in the evolution of life. The loss of the second moon would have eliminated these environments, potentially steering evolution in directions it wouldn't have taken otherwise. I know this sounds like we're venturing into the realm of wild speculation, but remember, we're talking about events that happened over billions of years. Small influences can have enormous cumulative effects when given enough time. So where does this leave us today? How are modern scientists investigating these possibilities, and what have they found? The search for evidence of Earth's lost moon is happening on multiple fronts. Astronomers are using increasingly sophisticated telescopes to scan the space around Earth, looking for objects that might be remnants of ancient cosmic events. The recent discovery of several quasi-satellites and temporary mini-moons has added fuel to this effort. One of the most promising avenues of research involves studying the chemical composition of lunar rocks in much greater detail than was possible during the Apollo era. Modern mass spectrometers can detect incredibly subtle differences in isotope ratios, differences that might reveal whether the moon was formed from material from one impact or from two separate collisions. In 2023, researchers at the University of New Mexico published a study that found unusual variations in the distribution of certain elements across the lunar surface. These variations don't match the patterns you'd expect from a single giant impact, but they do match some of the predictions of the dual moon theory. It's not conclusive proof, but it's exactly the kind of evidence that scientists hope to find more of. Meanwhile, space agencies around the world are planning new missions to study the moon and near-Earth space in unprecedented detail. NASA's Artemis program, which aims to return humans to the moon by the late 2022, will include sophisticated geological surveys that might finally provide definitive evidence for or against the dual moon hypothesis. The European Space Agency is developing the Hera mission, which will study the asteroid Didymos and its moon Dimorphos. While this mission is primarily focused on planetary defense, It will also provide valuable data about how small bodies behave in binary systems, information that could help us understand what happened to Earth's hypothetical second moon. But perhaps the most intriguing research is happening right here on Earth. Scientists are using advanced computer models to simulate the early solar system in incredible detail, running thousands of different scenarios to see which ones match the evidence we observe today. These simulations have revealed something remarkable. The formation of two moons after a giant impact isn't just possible. It's actually quite probable under certain conditions. Depending on the angle and speed of the impact, computer models suggest there's anywhere from a 20% to 50% chance that two moons would form instead of just one. That's a surprisingly high probability for something that most of us have never even considered. It suggests that binary moon systems might be much more common in the universe than we previously thought, and that Earth's current single moon setup might actually be the unusual case. As our investigation draws toward a close, I find myself thinking about the profound implications of what we've discussed today. If Earth really did once have two moons, it means that the night sky our ancient ancestors looked up at was fundamentally different from the one we see today. It means that the tides that shaped the earliest coastlines followed patterns we can barely imagine. It means that the gravitational forces that influenced the formation of our planet's geology, atmosphere, and possibly even life itself were more complex than we've ever realized. But here's what I find most fascinating about this mystery. It's not ancient history. It's not something that happened long ago with no relevance to our modern lives. If the dual moon theory is correct, then the evidence is still all around us. It's in the rocks beneath our feet, in the gravitational field that surrounds our planet, in the subtle wobbles of Earth's rotation, and in the mysterious objects that continue to be discovered in the space around our world. Every time astronomers discover a new quasi-satellite or temporary mini-moon, they're potentially finding another piece of the puzzle. Every time geologists analyze the composition of lunar rocks, they're searching for chemical fingerprints of this ancient cosmic collision. Every time physicists measure tiny variations in Earth's gravitational field, they might be detecting the lingering influence of a moon that disappeared before complex life even existed on our planet. I have to admit, this story has changed how I think about the moon. When I look up at that familiar silver disk in the night sky, I can't help but wonder about its missing twin. Was there really once a second moon sharing that dark canvas? Are there still pieces of it out there, following their own silent orbits around the sun? And I find myself wondering about the broader implications. If something as fundamental as the number of moons Earth has can be uncertain, what other assumptions about our cosmic neighborhood might be wrong? What other mysteries are hiding in plain sight, waiting for the right combination of technology and insight to reveal them? The universe, it seems, is far stranger and more dynamic than most of us imagine. We tend to think of space as empty and unchanging, but the reality is that it's full of moving objects, gravitational interactions, and the ongoing consequences of ancient cosmic events. We're not just observers of this cosmic dance, we're participants in it, influenced by forces we're only beginning to understand. So, did Earth once have two moons? The honest answer is that we don't know for certain, not yet. The evidence is intriguing but not conclusive. The theory is scientifically plausible but not proven. We're dealing with events that happened billions of years ago, and unraveling such ancient mysteries requires patience, sophisticated technology, and a willingness to question our most basic assumptions about how the solar system formed. But that's what makes this story so compelling to me. We're not just talking about abstract academic theories here. We're talking about the possibility that our understanding of Earth's history, and maybe even its present, is incomplete in fundamental ways. We're talking about the idea that there are cosmic influences on our planet that we haven't fully recognized or understood. The next time you look up at the moon, I want you to remember this conversation. Remember that what you're seeing might be only half of a much larger story. Remember that the object that has inspired countless poems, songs, and stories throughout human history might itself be mourning the loss of a companion that shared the sky for millions of years. And remember that the story isn't over. Every night, as Earth spins through space, it's still surrounded by the gravitational ghosts of its ancient past. Objects too small to see easily, but perhaps still large enough to influence the tides, the weather, the rotation of our planet, and maybe even the evolution of life itself. Whether or not the dual moon theory proves to be correct, it reminds us that our cosmic neighborhood is far more complex and mysterious than most of us realize. It encourages us to look up at the night sky, not just with wonder, but with curiosity about all the things we still don't know. The universe is full of lost moons and hidden influences, gravitational ghosts and orbital mysteries. And that, to me, makes it a far more interesting place to live. What do you think? Does the idea of Earth's lost moon capture your imagination the way it has captured mine? Have you ever noticed anything unusual about the moon, or wondered about the mysterious objects that share our corner of the solar system? I'd love to hear your thoughts in the comments below. Do you think there's something to this dual moon theory, or do you think it's just an interesting scientific speculation? Have you ever spotted any of those quasi-satellites or temporary mini-moons that astronomers keep discovering? And if this kind of deep dive into cosmic mysteries is your thing, make sure to subscribe to Javis Heist and hit that notification bell. We've got so many more incredible stories to explore, from the anomalous signals coming from deep space to the unexplained structures hidden beneath Earth's oceans. Trust me, the universe is far stranger than any of us imagine, and I can't wait to share more of these mysteries with you. Until next time, keep looking up, keep questioning, and remember, sometimes the most incredible stories are the ones hiding in plain sight, just waiting for someone curious enough to ask the right questions.